algebra with exponents and logarithms is probably one of the most challenging things that you're going to do algebraically in your first courses at university. So it's really important that you have practice and exposure to very specific things that can happen when you're dealing with exponents and logarithms. The thing I want to stress most of all, though, is there's nothing particularly magic about what we're going to do. This doesn't involve just incredible mathematical insight. What it really involves is just a very slow, methodical rolling out of your basic properties. So the golden rule of everything you do, really, is the following. So the golden rule. When you're doing a succession of steps, you want to make sure each one is simple, right? So each individual step an equality or an implication should be a property of algebraic operations. So my algebraic operations, and when I say that, what I mean is plus, minus, multiplication and division, or an exponent law, or a logarithm law. So the golden rule is to make sure that at every stage you're doing something very basic, right? You're not trying to jump through 10 hoops at once. You make sure everything is written slowly, carefully, follows logically. It's like reading a paragraph of text. You don't want it to be kind of a chain of thought. You want it to be kind of one step at a time, logically connected, and every step to be simple, relatively speaking. So this is kind of true not just with algebra, but for mathematics in general, and really anything. I mean, you want to have your arguments to be, the connections between the different ideas to be elegant and simple. So I don't want to show off by doing 10 steps at once, by staring into the sky and suddenly having a magical mathematical insight. I want things to be very, very systematic. So let's do an example, shall we? Let's do a bunch of examples. So let's do an example where we have to find an x to begin with. So find x, some number. Find x, some number, such that. So let's have the following. 2x minus 1 cubed is equal to minus 8. So what do I want to do here? Well, basically, I want to deploy my properties of algebra, exponent laws, or logarithm laws to kind of undo this. And the basic plan is always, you've got an equality, you want to do the same thing to both sides, that keeps equality going, it's one of these fundamental principles, and you want to do it in such a way that it kind of unravels each piece. So when I look at this, the first thing I think to myself is, well, I've got an exponent, right, straight out the bat, so I've got this expression, and the base is a variable, 2x minus 1, it can change, but the exponent is constant, right? So this kind of tells me a few things. So let me just talk about my thinking. So I'm going to really carefully highlight all of my thinking at each stage here. So what I'm thinking here is my exponent is a constant. So the 3 is fixed. That's the first thing. So it feels to me that because it's a constant, I should be using laws of exponents to kind of undo this cubing. So I feel like I should use exponent laws to somehow manipulate this to get x on its own. So the first thing is, if I'm taking something to the power cube, how can I undo that? Well, I could take a cube root. So let's get this going. So let's start with the original statement. It's a good idea to write that down. That's my starting point. So this would imply, this is the implication symbol, of course. This would imply that if I take the cube root of both sides, which is completely fine because you can take cube roots of anything, remember, because 3 is odd, it stays the same. So let's do that. So let me get it correct. So I take the cube root of both sides. Okay, so this is true. Next, or what do I know? Well, at this point, taking the cube root, one of my laws of algebra says the following. It says that if I take b to the power a to the power c, then this is equal to b to the a times c. Right? This is the reason I'm taking a cube root, because if I multiply 3 by a third, I'm going to get 1, and anything to the power 1 is just equal to itself. So this implies that 2x minus 1 to the power 1, which is on its own, has to be equal to the cube root of minus 8. So it's not completely obvious what that is, but if I take minus 2 and multiply it by itself 3 times, I get minus 8. So this is minus 2. So next I need to use algebra to get x on its own. So what should I do? Well, at this point, I'm going to use, what should I use? I should use my usual thing that I've used before, kind of my law of, my property of just algebraic operations. This implies that a is equal to c minus b. Okay, one of my kind of absolute core pieces of information. So this implies what? This implies that 2x would be equal to, adding 1 to the other side would give me minus 1. So minus 2 plus 1 is minus 1. Finally, divide everything by 2. I get half on this side. So this, if you want, would be this. So what have I just done? That's this. And this at the bottom is the property that a times b is equal to c. Implies a, well, b is equal to c divided by a. If I'm going to use the same notation, where a can't be equal to 0. So I've done it, right? I've done it. And something to be aware of is that every one of these is an if and only if condition. So this is exactly the same statement as this. So it kind of all goes backwards. That's if and only if this. That's if and only if this. That's if and only if this, because cube roots are unique. All the rest. So very nice. We've completely solved this problem. Now, something to be aware of here that I see an awful lot of when we're doing algebra is not really thinking consciously about what all the symbols mean. So, for example, something I see all the time is instead of using this symbol, people, I'm going to do this in red because it's horribly wrong, people use this symbol. They just write a string of equals. It's almost like it's an unconscious thing. You just write equals, 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 equals. You don't think about what you're doing particularly. And internally, you're probably not literally saying they're equals, but that's what you're writing. And this is totally wrong, isn't it? Because minus 8 is equal to that. It's not equal to that. These are not equal to each other. So you need to be careful about using the correct symbols, right? If you have two quantities that are the same, then it's an equals. That's the only occasion you use it. But if one statement implies another statement or is equivalent to another statement, then you need to use the if and only if symbol. Okay, so just writing a string of equals is a real demonstration of messy thinking, right? When you're writing sentences, right, you just don't write the same word between every sentence just for the hell of it, right? You don't write and between everything, right? It might be appropriate for some things, but you don't have and between every other word. It's just crazy. It's the same thing with equal signs. It's a terrible temptation just to write equals, 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 equals blindly. Be conscious about it, right? You're trying to write something down which is logically sensible. It's almost like something you could read or you could write in full words, right? This is the statement that 2x minus 1 cubed is equal to minus 8. That statement is equivalent to the statement that this is true. That this is true. And then I say, well, that statement is equivalent to this statement by this law of exponentials or exponents. and I keep doing that. So this is something that you could kind of write in full words if you wanted, right? And you want it to be readable in that way. You want it to be very obvious what each step is. It's no good coming up with a solution and just not being able to express it to somebody. It's vitally important that other people looking at your work can understand it, because ultimately you're going to be using mathematics in the sciences and all sorts of other things, and if other people don't understand what you're doing, it's for nothing really. So this is a skill we've got to get good at. Let's do another example. So let's do the following. So one that looks kind of grim. So let's find, so these are examples taken basically from real kind of midterm type things, right, for calculus classes. So they're the kind of algebra you'd be expected to do. So they're quite difficult. So find x such that, and if you find these difficult, you shouldn't feel bad about it, because these are difficult examples. Most people will struggle with these, but we're going to go through them carefully because it's important that you see how to do them really properly. So imagine this. Find x such that the following horror is equal. So this gruesome expression is equal to 3. Okay. So it feels kind of like the same business as above, right? I can see square roots. I can see things to the power 3. Those are all constant exponents. So I think we basically probably have the same logic. It worked before. Down here, it feels like we should be doing the same basic things. We should be using, so now there's a few exponents, but I think we should be doing the same thing, right? This is me thinking out loud to myself, right? It feels similar. Okay, so this left-hand side is really gruesome. It's confusing. What should I do? Well, what I really need to do is to simplify the left-hand side into some expression to some single power, if I want to use the laws of exponents like I did before. So let's take the left-hand side and try to simplify it. So what's the left-hand side equal to? It's equal to this. Now, what laws of exponents do I know? Looking at this, the 2x plus 4 and the x plus 2 on the bottom are not so different. They only differ by a factor of 2. But before I do anything, let's write things purely in exponents, because I think this is a good plan, right? So purely in terms of exponents, it would be this. So I don't like the square root. Let's get rid of the radical symbol, because it kind of doesn't work well with the top, the numerator. All right, so I've got this. So this is really annoying because the base on top of the exponent is 2x plus 4, and the base on the bottom is 2x plus 2. They're different. So if I want to apply a law of logarithms, I really need them to be the same. So in my mind, I'm saying to myself, I want to make the bases the same. Bases equal. Now, can I do that? Well, thankfully, from the setup, I can, because 2x plus 4 is just x plus 2 multiplied by 2. So I can bring out a factor of 2. This wouldn't necessarily be possible, but it is in this situation. So this is 2 times x plus 4, all to the power 3, all divided by x plus 2 to a half. Okay, so now what am I going to do? So at this point, so you've made a mistake already, transcription error. Should be a plus 2 here. So this is the distributive property. I'm not going to write that down. In fact, yeah, let's do it. Why not? Let's do every single step. So this is the distributive property. Okay, so got that. Next, well, I've got a product. So if I look at the numerator, I've got a product of two things to a certain power. So now what do I know? I know that I can apply one of my laws of exponents. So this becomes 2 to the 3 multiplied by x plus 2 to the 3, all divided by x plus 2 to a half. So what's law is this? This guy is the law that a, let me get this right, this is ab to the power c is equal to a to the c times b to the c. That's that law. Okay, now what? Well, at this point, I can write this in a slightly less irritating manner. Let me write this as 2 to the 3 out the front multiplied by this ratio. See, I've managed to make the exponents the same. Again, let's make sure we know what the algebra is. The piece of algebra here, what is it? It's a b over c is equal to a times b over c. Okay, so maybe if I put a bracket there just to really hammer home the point. But now I've kind of done what I needed to do. I've made the bases exactly the same. And at this point, it's a ratio of two things, and the bases are the same, so it's going to be a difference of the exponents. So this is going to be 2 to the 3, which is 8, times x plus 2 to the 3 minus a half. Oof. So 3 minus a half is what? It's going to be 6 minus 1, so it's going to be 5 divided by 2. So at this point, in fact, let me make sure we've written down what the laws are. So what I'm invoking here is b to the a divided by b to the c is b to the a minus c. So you see every step is a simple property or log law, or in this case exponent law. So what do I have? Well, now at this point it's going to be 8, write that a bit neater, 8 times x plus 2 to the power 5 divided by 2. Is that correct? So we've simplified the left-hand side. And notice something here. I've not set this equal to 3 or anything yet. I've done the left-hand side completely separately. That's a really good plan. You don't want to kind of just write down the equation and start manipulating it necessarily, not if you're going to have to do something quite complicated. So it's a good plan just to isolate each piece, or in this case the left-hand side, and do it completely on its own first. So simplify the left-hand side first, separately. It's really good practice to do this, right? Don't have the equality yet. So now at this stage, what do we have? Now I can kind of swoop back into my actual equation. So I'm trying to solve the equation at the top here. So I'm trying to solve this. So if this is true, this is if and only if now, 8 times x plus 2 to the 5 over 2 is equal to 3. So I've converted the problem into a much more reasonable problem. And now if you think about it, it basically looks exactly the same as the problem we saw before, pretty much. So we could rearrange this now. So this is if and only if x plus 2 to the 5 over 2 is equal to 3 divided by 8. So again, let's be super duper careful. Every stage I want completely justified. So what property is this? This is the property. So this is the property that if I have a times b is equal to c, this is if and only if b is equal to, how will I write it down? Yeah, c divided by a, assuming a is not equal to 0. So sorry, that's a little bit small, but it's one of these ones we've used over and over again. So now how do I get rid of the exponent? I take everything to a specific power. And this one's a bit more complicated because it's to the power 5 over 2. But the trick is to raise it to a power that makes the power on the left-hand side 1. So what I should do is raise it to the power... I should raise this guy to the power 2 over 5, I think. 2 over 5. So let me just write this carefully. So I'm going to take both sides, raise them to the power 2 over 5. So raised to the power 2 over 5, that's going to be equal to 3/8 to the power 2 over 5. So this is if and only if what? So now what do we have? We would have x plus 2 on its own has to be equal to 3 over 8, 2 over 5. And this now is if and only if x is equal to, x is equal to what? X is equal to 3 divided by 8, 2/5. So let me get this right. Minus 2. So again, let's just label everything super duper carefully. So here we are invoking, as we did above, the fact that b to the a to the c is equal to b to the a times c. And here we're just invoking the fact that a plus b is equal to c if and only if a is equal to c minus b. So we're going through this incredibly carefully. And we could continue to simplify this if we want. It's not actually so important. Maybe we'll do it. Maybe we'll do it just for a bit of practice. So this is if and only if x is equal to, well, we can square everything first and then take a fifth root. I suppose it would be 3 squared divided by 8 squared power 1 over 5 minus 2. So that's again just my laws of exponents, or really my definition of powers. This is if and only if x is equal to, so let's write this finally in radical notation. Like I said, this is kind of unnecessary because this is the correct answer. We've finished, but it's quite nice just to do this as a little bit of practice at the end. So that simplification isn't truly necessary in my opinion, but it's good practice to be able to do it. Okay, that is a difficult example. It's especially exhausting when you go through every single detail. Now, over time, with practicing these kind of things, you're going to get, so let me zoom out just to see everything we've done. Yeah. Over time, you won't have to go through absolutely every step like this. You'll be able to maybe trim out 1 or 2, but I would strongly recommend getting in the habit of writing down answers this carefully. Certainly whenever I set tests or exams or things like this, I write solutions which are this level of detail. So I'm assuming you are going to go into this kind of level of detail. I don't assume that you're going to write all of these kind of comments. That's a little bit too much. But I expect the step-by-step guide. So when I write solutions to my own test problems, for example, they're going to look something like this as an example. Okay. So tricky, right? Not easy. Let's do another piece of algebra with exponents, which causes a lot of problems. I kind of want to go through a few examples. So like I said before, this is hard algebra. This is not simple algebra with exponents. This is difficult algebra. This is the most difficult type of algebra you might get in your lower division classes. So let's make some observations. So let's do the following. So imagine if I take 5 and I square it, and then I take the square root of that whole thing. Bit of a funny thing to do. But we know what this is equal to. This is equal to the square root of 25, which is 5 back. Okay, so taking a square and then a square root seems to give you the number back. However, what happens if I did it with minus 5? So if I took minus 5 and I squared it, what do I get? Minus 5 times minus 5 is 25. Oh goodness, it's back to 5. Remember, this square root notation is always positive by convention. That's the decision we made when we were thinking about exponents. So this is not equal to minus 5. So this is kind of a bit of a pain, right? This means something nasty is going on. Now in particular, it is kind of related to -5, but only as a negative. So this is equal to what? This is equal to minus of -5, but that isn't equal to -5 itself. So this business of squaring and taking a square root, really what it's giving me is giving me the absolute value. So the size of the number. 5 and -5 are the same size, and really they're the same distance from 0 if you're thinking about the number line. So the conclusion of this is the following, and this is something we're going to look at in more detail when we're doing absolute values, but I want to preview it now because it turns up. If I take the square root of a square, so this is equal to, well, it depends. It depends if x is positive or negative. So to talk about this, I'm going to use something called piecewise notation. So piecewise notation is when you have something which is defined in two different ways depending on a certain set of circumstances. So this is kind of piecewise notation, it's called. Piecewise notation. And it depends on the value of x in this case. So what is it going to be? Well, if x is positive, it's just x back at you. Unfortunately, if x is negative, it's not. It's minus it, as we've just seen above. Now that's confusing because you might think, well, but wait a moment. The output of a square root is always positive. It can't be minus x, but remember x is negative, and negative of a negative is always positive. So this should actually be a familiar expression to you. If I take a positive number, then the absolute value is just the value of the positive number. But if I take a negative number, it's negative of it. So this is the absolute value of x. Again, something we're going to look at in more detail in further videos. So this is for all real numbers x. So this is a measure of the size of a number. So this is important. This tells you that it's not as simple as you think. This is not equal to x. And it is confusing because here's just the wrong logic. So I talked about this in the laws of exponents video, but it's so easy to think that, well, it's x squared to the power of a half. So this has to be equal to x to the 1, which has to be equal to x. This only works, right? Only works if x is positive. Remember my laws of exponents. I need the base to be positive a lot of the time, otherwise they'll fail. This is exactly the problem. If the base is negative, it doesn't work. So it's terribly subtle. You've got to be really careful. So the square root of a square, it makes sense for any number because when I square any number, it's positive. So I'm always taking the square root of something positive or potentially 0. I can express the absolute value in this format. So this is kind of an interesting way to do it. So let's do an example involving this. Let's do a couple. So here's a tough one. So express absolute value divided by root x squared plus 1. It's nice it's x squared plus 1 because it's always positive. In the form, so I want it as a rational expression all to some power. So this is rational, ratio of two polynomials, and this r is some constant. Oh my goodness. So you look at this and you're like, well, that's square root, the absolute value. It's bad, right? What are we going to do? And I don't blame you for thinking that, right? This is a difficult example. It's not obvious that it falls into this pattern, but remember, we do know the following. We know the absolute value of x, so this is the numerator. I'm thinking about this totally separately, is equal to the square root of x squared for any x. So that means I can take this expression, so that implies that I can take this expression and rewrite it in this format. And this looks nice to me, right? Because now what do I have? Well, this feels now very similar to one of my properties of exponents. Namely, if I take a quotient of the same radical of two things, then I can bring the bases together. So this is equal to square root, everything's positive, so I don't need to worry about anything, thankfully, of x squared divided by x squared plus 1, all inside the square root. Okay. So let's make sure we understand what property I'm using here. Well, in its broadest sense, I'm using this property really. I'm using the fact that a to the c divided by b to the c is equal to a over b to the c. That's the property I'm using here in its broadest sense. But if c is equal to a half, then I'm just taking square roots. So I'm just, in my mind, interchanging everything. But now at the end, we should make the time to write this down in a format as we are requested, which is a rational function, which I've got now, all to the power of a constant. So this now is equal to x squared divided by x squared plus 1, all to the power of a half. So we're done, right? At this point, we've got my px over qx, and this is a perfectly valid r. So pretty neat piece of algebra. The reason this is important is because you might be asked to do something specifically with an expression like this, and it may be impossible to deal with given the way it's written down. But if you write it in that new format, it may be possible to attack it using the knowledge you have. So very, very important. Let's do another example, a really difficult one. So this is taken from, or very similar to a midterm question in one of these first calculus classes. So it wasn't quite like this, but this was kind of a step in it that was required. So here's a really tough one. So if x is strictly less than 0, so negative, express, so I'm going to do it like this, 9x squared plus 1 all to the power of half over x in the form some constant a with the same story as above, some rational to some power. Okay, so exactly the same as above, but now I've got a constant at the front, so it's a little bit more. Yeah, so so one thing to notice here is 9x squared plus 1, it's always positive, right? Because x squared is always greater than or equal to 0, so timesing it by 9 and adding it to 1, it's certainly going to be strictly greater than 0. So that means I'm not taking square roots of negative, so it's fine. If the problem was this, then it would basically be identical, wouldn't it? It would be the same deal. I would write down the base, the denominator as the square root of x squared and I'd be done. But it's not. It's not equal to this. But there is something being given to me here. I'm being told that x is strictly less than 0. So let's think about this. So here's an issue. So the problem is the following. So I do still want to do the same kind of logic. I want to replace x with some square root of a square. But the issue is the following, as I said. x squared to the power of half, so the square root of x squared, that's equal to the absolute value of x, isn't it? But that is not equal to x, okay, if x is negative. It's not correct, is it? It's out. It's out. However, what do I know? Instead, x squared to the power of a half, well, it's equal to the square root. No, it's equal to the absolute value. That's true, but that's equal to minus x. Okay, and let's just make sure this is correct. This is very confusing. So, e.g., if I have minus 5 squared to the power of a half, that's equal to what? It's not equal to minus 5, it's equal to minus of minus 5. It's the logic we saw above. So in this story, x is minus 5. So I know it looks confusing with a negative, but it's there. So what does that mean? Well, that means that x itself, so I care about x here. So this tells me that x is equal to minus, so let me just get this right, x is equal to minus x squared to the power of a half. Very confusing. But that's not bad, is it? Because now I can swoop in and feed this in. So all of this tells me that this expression at the top this guy up here, so let's get this going, is equal to, okay, well then let's replace the base by minus of x squared. So this would be 9x squared plus 1 to a half divided by minus x squared to a half. Okay, but now what do I know? Well, I could take the negative all the way out the front. So this could be written as minus 1 multiplied by 9x squared, sorry, let me get this correct. 9x squared plus 1 to the power of a half divided by x squared to the power of a half. And now I'm in exactly the same logic as before. This becomes what? This is minus 1 at the front, that constant, multiplied by 9x squared. Everything's positive, so I can do this. X squared all to the power of a half. Bingo. So what do I have? Finally, I have a as minus 1. I have this as px over qx. And this is my r. So let's just zoom out a bit to make sure we can see this whole thing in one go. Serious example. Let me just talk through it one more time. So if I want to express this in the format a times a rational all to 1 power, I basically need to express the bottom here as something to the power of half. And to do that, I'm using the fact that x squared to the power of a half is the absolute value. The problem is if x is negative, so this is absolutely crucial at this stage, right? At this stage, x is negative. If x is negative, it's not equal to the absolute value, it's minus of it. So that means when you're replacing the bottom with something with a square root, you've got to take the negative. So really, really subtle. Then the rest is laws of exponents done very carefully. So yeah, this is a really difficult example. This is one of the most difficult examples you could see, but I think it's good to see as hard as it gets, really. So you're not surprised when you see things like this a little bit later on. The main thing is, you may look at this and think, I could never do this myself. That's not true. What's true is, if you look at examples like this, and you'll get practice in doing them, if you look at examples like this and make sure you kind of stay focused on each moment, the steps in each moment, over time, the overall pattern will become very clear to you and you'll be able to do it. But if you don't understand every moment in this, so these moments here, well, these are very important. If these don't make sense to you, then you will never be able to truly understand or you'll never be able to do problems like this. So you need to just be very, very granular about it. You've got to be focused on the details to do this. And this is kind of a good example. It's kind of the hardest example I can think of, really, with this type of algebra. So just as an overall conclusion to this, when dealing with these types of expressions, all of them have had the same basic pattern. We've had bases that involve variables and exponents that are constant. So, just as a broad conclusion, when dealing with expressions, so maybe I'll just say, when dealing with expressions, there are exceptions to this, but when dealing with expressions with constant exponents, overwhelmingly you're going to be dealing with exponent laws. There are exceptions to this, of course, but if you see constants, you're going to be doing things like raising to specific powers to undo them. So this is kind of just a very broad statement, something to be aware of. And again, the reason this is important is because it's not just as an exercise to manipulate expressions into weird formats. It's not what this is about. You're going to have expressions that you need to understand in huge detail, much greater detail than you're used to. And in order to understand them, you'll have to put them in a specific format that makes them more amenable to study. And doing that involves this type of algebra. So it's not just as a brutal exercise in the most complicated ways you can put together your simple rules. It really is vital to studying complicated expressions.